I will make it sort of very, it should be possible to follow, so I introduce every single definition, should be clear, but say if there is something that is not familiar and that you struggle to follow. So the model K spaces to keep in mind are high rank symmetric spaces of non-positive or non-compact type. And two earlier papers in this project already exist. So one is written with Urs Lang and Bruce Kleiner, and the other one is written with Urs Lang and a previous doctoral student, Tommaso Goldhirsch. But they take a more analytic approach in terms of metric currents, which is much more advanced, whilst the paper I will talk about is much more elementary and has some kind of combinatorial flavor, let's put it this way. So the goal is to provide some high-rank analogues of Gromov hyperbolicity. But to give a system or a systematic treatment of high-rank analogues, we need an appropriate definition of higher rank. And in this setting, this will be the so-called asymptotic rank, which is defined as follows. So it's the supremum over all integers for which there exists a sequence of scale factors that go to infinity and a sequence of subsets such that when you look at the sequence of rescaled sets, which you think about as getting larger and larger and you sort of rescale them to unit size, then you want this to Gromov Hausdorff converge to something like a typical n-dimensional object. So there are several equivalent definitions or different choices that leads to the equivalent definitions. But we can take the unit ball in some n-dimensional space. So intuitively, we are looking for larger and larger sets such that when we rescale these appropriately, they should converge to something n-dimensional. And this goes back to Gromov, and that was further investigated by Wenger, de Combe, and Kleiner. And it is a quasi-geometry variant. And I do realize that it's very hard to understand what this definition actually means. So I would like to give some examples to make it more bearable. So if X is a cat0 space, or you can be slightly more general and look at a space with a conical geodesic bicombing. So we need this for later. So let me tell you, it's sort of a weaker convexity condition. So a space has a conical geodesic bicombing, meaning that, or it is a conical geodesic bicombing is a map that for every 2 points in your space, it selects a constant speed minimizing geodesic, connecting them, such that so this sort of inequality, this convexity inequality holds. So it does look, it's not slightly the same as convexity, because then it would also require it to hold for subsets, but it's almost. So this condition is satisfied for cat0 spaces, or for example for Busemon convex spaces. Yes, you can take it away as a notion of, or a weak notion of non-positive curvature. And then if X is now proper and co-compact, then in the first case, so if X is a cat0 space, then the asymptotic rank is the maximal n for which X contains an isometric copy of Rn, so an n flat, or in case that it just has a conical bicombing, then the asymptotic rank is the maximal dimension of some non-n-dimensional space contained in it. Right. Okay, there you go. So, I would like to introduce a sample result from this paper with Kleiner and Urs as a sort of sample result of high rank hyperbolicity. And then I first need this definition. So a metric space is said to have the so-called slim simplex property if for all lambda and c constants, there exists some other constant d, such that if you take Euclidean n+1 simplex, so that will be a simplex in Rn+1, right? The convex hull of n+2 points in general position, and you take a map defined from the boundary of this triangle delta to X, whose restriction to each facet is a quasi-symmetric embedding. Right, so how to say this nicely? You're in a setting of like a higher rank setting of quasi-geodesic triangles. And then you want that the image of every facet is within the D neighborhood of the image of the union of all the other facets. So this should remind you of the slim simplex property in Gromov hyperbolic spaces, but now more complicated. So basically, this here. Every facet should be in the D neighborhood of the image of the union all the others. And yes, you can sort of take it away as a definition of high rank hyperbolist, even though that doesn't really exist. Think about it as this way. And the result I would now like to state is the following. So if X is a proper metric space with such a conical geodesic bicombing, then the asymptotic rank is less or equal to n if and only if X satisfies this slim simplex property with some explicit constant here. And this would then further generalized in the paper with Tommaso. Namely, it can also be formulated for classes of metric spaces. So if you take a class of such metric spaces, so in the definition of asymptotic rank, you take subset in different members of the class by taking a sequence in the class and then subset in the corresponding elements of the sequence. And now if every set has, every space has the slim simplex property, the result holds uniformly for the whole class if every space has the slim simplex property. So in particular, if the class is defined without any further parameters, then this constant will not depend on X anymore. That's the whole idea. Right.
In the uniformly comes with the fact that the constant in the SSN are fixed.
Yeah,
so,
yeah,
okay, good.
yeah.
You're fixing the end.
So yeah, and then the idea is to get rid of this X, right? Yeah. Yes. So the focus on our investigation has been to come up with a high rank analog of this Gromov's quadruple definition of hyperbolicity. So this was now the high rank analog of the slim simplex property. I will talk, make a more introduction to this later if it is unclear. But now we are focused on the quadruple definition. How can we generalize this to higher rank? What makes sense to do?
Right. A question.
Yeah.
What is the quadruple definition?
I will come back to it. So, have you heard about Gromov hyperbolicity?
Only in name, but not. I don't know the definition.
Okay, it will become clearer.
Okay.
If not, then yeah.
But this is a statement for for this basis for with conical geodesic bicombing. Yeah.
Yes.
So this,
It's right. But now I will know before I can start to do anything. I need some more definitions. So I would like to talk about injective metric spaces. So a space is said to be injective if every one Lipschitz map defined as some subset A of metric space B has a one Lipschitz extension to B. So A and B could be anything. So this is in accordance with the notion of an injective object in category theory. So it's a category of metric spaces with one Lipschitz maps as morphisms, or it's also the same as being an absolute, like a one Lipschitz, how do you say it? An absolute one Lipschitz retract. So it means that there exists a one Lipschitz retract of every metric space containing it. Or if you're familiar with the notion, it's the same as having the Helly property, which is also known as hyperconvexity for geodesic metric spaces. So if you take a family of pairwise intersecting poles, then the whole global intersection has a common point. That's not so relevant, but some examples are R, complete R trees, L infinity space for any set S. And here are some properties. So every injective metric space is complete and has such a conical geodesic bicombing that is also reversible and equivariant. And in fact, it holds that every metric space has a so-called injective wall. And this was discovered by Isbell in '64. And what does it mean? So every metric space is contained in a smallest injective metric space in the following sense. So E of X is injective, and then there is an isometric embedding little e, going from x to e of x. And it satisfies the universal property that for every other injective metric space that x is contained in, every such map must factor through the injective hull. So it might not be very easy to see like what does this even look like. Okay, it's very abstract, but in fact there is a very nice, explicit, easy construction that was like by Isbell, and I would like to go through it just to give you some more intuition of what we are talking about. So so you look at the set of real-valued function which satisfies the following property. So sort of similar to the triangle inequality. That's what it should remind me of. So the idea is to extend your space such that the new points in your space are functions on the space. And the value of the function at the point x, so f of x, is exactly the distance between f and x. So f of x is equal to the distance between f and x in the new space. And now you take a natural ordering on the set delta, and the injective hull is precisely what is written here. So that's the minimal elements of this set here. That's what it comes from. And so the metric on the injective hull is the L infinity metric. And now, yeah?
What is the ordering?
Just a natural ordering of functions. So f of x is less equal to g of x if it's pointwise that way. Yes. And yeah, so the metric on the injective hull is just the infinity metric. So usually this, what do I want to say? So usually the elements of the injective hulls are not bounded. Like typically they're not. The injective hull could be absolutely huge, tremendous. But the difference between any two functions is always bounded. So that's why I can use this metric. And the canonical embedding is just sending each point to the distant functions to the point. And some properties, so if x is compact, so is also the injective hull. This is just Hausdorff. And if x is finite, then actually the injective hull is a very nice finite polyhedral complex of dimension that's equal to half times the cardinality of x, with an infinity metric on the cells. So here are some examples. So if n is equal to 2, then so you have a metric space of 2 points, then the injective hull is a line. If n is equal to 3, then the injective hull is a tripod. And if n is equal to 4, then the injective hull is these sort of tilted rectangles with antennas. And now for n is equal to 5, there are already 3 different types of combinatorial, like 3 different possible combinatorial types of injective hulls. And for n is equal to 6, I thought we were talking about hundreds. And this is a computer generated, like how to do it. Like you don't want to do this by hand. Right, so now I've been talking about a lot of things, but none of it's really related, so I'd like to start to tie things together. So here's like a key observation, like the following items are equivalent and we will need them later. So a metric space, for a metric space, a general metric space, the following conditions are equivalent. So x embeds isometrically into a tree, so that's just a geodesic metric space where every geodesic triangle is a tripod. Or it satisfies, the following quadruple definition, which should remind you, if you're familiar with Gromov hyperbolicity, this should be quite familiar. And the final item is the following, so the combinatorial dimension, which was introduced by Dress in '84, so 20 years after Isbell, of x is at least, or is at most 1, and it's defined as, so you look at the supremum of the dimension of the injective hull of finite subsets of x. And remember, if x is finite, then the injective hull had a nice polyhedral structure, so this makes sense to talk about the dimension. So the finite subset, you can think about the dimension of the injective hull is a rough measure of the complexity on the metric of this finite subset. Right, so this here now has two nice generalizations. So the first one is the Gromov hyperbolicity. So if I now take the second statement and I add plus to delta, then X is said to be Gromov hyperbolic if and only if it satisfies this quadruple inequality that I was talking about earlier. And for geodesic metric spaces, it is equivalent to the so-called slimness of quasi-geodesic triangles. So every side of a geodesic triangle should be contained in the delta neighborhood of the union of the other sides. And think about the tree. So before we had the metric tree, which was equivalent to the this here condition without the plus 2 delta. And now then I have the tripod. So now I like extend by delta, and I get plus 2 delta here. So that's sort of the relation if you think about it. I like to see the equivalence where this comes from. Or on the other hand, Dress proved in 1984 the following generalization of the combinatorial dimension. So X is said to have combinatorial dimension less or equal to n if it satisfies this certain 2 times n plus 1 inequality. So you fix an index set, which like any could work, but we like this one because it has this what do you call it, nice involution, and namely just changing the sign. And then the combinatorial dimension of X is less or equal to n if for all family of points in the space indexed by this index set, there exists a permutation, alpha, that is not equal to minus the identity such that this inequality holds. And then we thought, when we wanted to find a generalization of the quadruple definition of Gromov hyperbolicity, we sort of just did the naive thing and said, okay, what happens if we combine the two? Yeah?
Could you just explain on the picture what is like, how is it related to the inequality? Like, what is X? What are the lines? I don't understand what it is.
Okay, so it's not, okay, the proof is that you would have to do the proof, but I wanted to just quickly say that before here, if I can go back. So before, just to see slightly the relation, why it's like this delta extension, right? Before here we had this quadruple definition point, and that was the same as X embeds into a metric tree. And now I added plus 2 delta 3, so a tree here is a tripod, right? What is a tree? It's a geodesic metric space with every triangle is a tripod, right? And then I get this inequality. So now I sort of extend by delta plus 2 delta here, and then I don't have a tripod anymore, but I have triangles that are not allowed to be very flat. So all the sides are in a delta neighborhood of the union of the others. It's just to see, okay, it's not the formal proof, but just to see slightly the relation, but yeah.
What if delta is big? Because you don't have like a...
Well, you wouldn't really, you can talk about big delta, but the point is usually that delta is small, right?
No, delta is big. Delta is big, but delta is frank, that's delta.
Yeah, okay, you're right. Okay, delta is delta, it doesn't matter. So for basically,
this was for every part, for every
delta, right?
Yeah, and for every x, y, z.
Yes, exactly.
Very far away point.
So for small scale, maybe this doesn't mean anything, right? For small scales, this can be totally irrelevant, but for large scales, then it starts to matter. Does that make more sense?
Yes.
Okay. Otherwise, I could go through the proof with you later, but it wasn't meant to be anything very. Don't pay too much attention.
I just was wondering how the picture, like what is X or Y or Z.
Oh yeah, okay, yeah, okay. I can go through it with you later, but that's not so relevant right now.
Yeah, the picture is not meant to explain the quadruple.
No, it's not. It's just.
Well, you can put so you take the 3 vertices and then the 4th point W, you put one on one of those sides.
Yeah.
So W is like in the middle of one of the sides.
For instance, yeah. And the other 2 are.
Yeah.
This might be trivial, but if this inequality is true for any delta, then you can conclude that the space is a tree, or not necessarily.
Well, yes, if delta is equal to 0, you get the tree. Then you get that X is 0 hyperbolic, which means that delta here is 0, so you get the tripod. For every geodesic triangle, it's a tripod, which means that it is a tree. Yeah. Okay, so what I want to come back to now is the actual definition. We have sort of made our way through all the definitions, and we say that X is an n, delta hyperbolic, which is a new definition, an experimental definition, if it satisfies this inequality by Dress with plus 2 delta on this side. And so that was the idea. my supervisor told me, yeah, see what happens when you do that. And it turns out that this is actually a very good idea. So here are some first observations, just to give you a feeling of what happens when one does that. So every n, delta hyperbolic space is also n prime, delta prime hyperbolic, so if you just scale it, it works. X is 0 hyperbolic, X is n, 0 hyperbolic, if and only if it has combinatorial dimension is equal to n, so that's just by dress, you take away the delta and there you go. X is 0, delta hyperbolic, if and only if it has the diameter less or equal to delta, because the only permutation of 2 points that's not equal to minus the identity is the identity. And then you take this inequality and it comes out of it. So X is 1, delta hyperbolic, if and only if it's Gromov hyperbolic. So it turns out that this inequality of sums is just a very bad formulation of the quadruple definition of Gromov hyperbolicity. Which is nice, this is what we wanted. And it behaves very well on the L infinity products. So the L infinity products of two n delta hyperbolic spaces is n1 plus n2 delta hyperbolic. So in particular, if you take n delta Gromov delta hyperbolic spaces, then this product will be n, delta hyperbolic, which is nice. And n, so I denote by star here that it is some delta, is preserved on the rough isometries. So a rough isometry is the same as a quasi-isometry, but the multiplicative constant is 1. So it's quasi-isometric invariant for a certain class of spaces that I will come back to later, namely the class of coarsely injective metric spaces, which I guess you can almost guess what it is, but we'll come back to it. And the asymptotic rank is s equal to n uniformly for all n, delta hyperbolic spaces. And also you have that every asymptotic cone of a sequence of n, delta hyperbolic spaces is n, 0 hyperbolic. So these are just scaling arguments basically. Right. So far I've talked about that anything holds for a general metric space X, but you can take the injective rule as a regularization of any such general metric space, and it's a very, very efficient way of embedding a hyperbolic or a general hyperbolic space into a hyperbolic space which is nice, geodesic, contractible, right? And here are some further results, or like a first result, an actual theorem. So the following are equivalent. X is n, star hyperbolic, is equivalent to the injective rule being n, star hyperbolic, and here is actually for the same delta, which is a generalization of a result for Gromov hyperbolicity, right? So if X was Gromov hyperbolic, then also the injective rule would be Gromov hyperbolic. But here we have a generalization. And the asymptotic rank is less or equal to n for the injective rule. And the final property just says that there exists a constant such that X contains no isometric copy of the L infinity cube, like n in n plus 1 dimension for large enough radius. So essentially, the last property just says that X is n, delta hyperbolic if the injective hull does not contain any large copies of n plus 1 dimensional space. And then we just use these balls to sort of quantify it.
So it means E of X does not contain a copy.
Yes, E of X.
Yeah.
E of X, yes. Sorry, that's a typo. That's definitely a typo. But what about the slim simplex property that I was so on about in the beginning of the talk? It turns out, yes, exactly. It turns out that every n, delta hyperbolic space satisfies the slim simplex property without any further assumption. Which is again nice because you have the equivalence between the slim simplex property and the quadruple property in Gromov hyperbolic spaces. And here again we have a nice equivalence.
Question.
Yeah?
The slim simplex property, it doesn't depend on delta. Right?
No. So
there is no delta inside.
no, we talked about the D neighborhood, right? The slim simplex property is a higher rank analog of this delta version for Gromov hyperbolic spaces. Does that make sense?
And what is the slim simplex property again?
Okay, so in the beginning...
It's the same as the picture with the triangles, only you have faces of the simplexes.
Yes. So that makes... When I talked in the beginning of...
Yeah, I think maybe your point is so that on the right hand side, so you don't have a constant, but on the left hand side you have explicit. Yeah, is it your point? So that they have some n delta, there's now some delta, and on the right hand side you have just n. But this simplex property, so there is some constants in the definition. So there is some.
I think I'll ask this question later.
Yes, I can look up the slim simplex property with you again. Just think about it as a higher rank version of the slim simplex property. Yeah, okay.
I think slim triangles. Yeah.
Yes,
so all its
exactly.
spaces slim triangles, and now you move up a dimension. Look at the simplex.
Slimness has a certain parameter, right? So what is?
Yeah, but there is more parameters because you have to pick the quasi-isometry constants first that determine your faces, and then the thinness d depends on those, and on the
But the thinness d can be compared to the delta, right? That's the sort of what you want to do roughly. Okay. Anyways, what about the converse statement, right? We want something the other way. That's we want an equivalence. And it turns out that this works for a certain class of metric spaces, namely coarsely injective metric spaces. Those are very nice, and we want to talk about them. Well, what I wanted to say first here is that for the proof of this here, so how does it work, the proof? Is that it uses this uniform version of the slim simplex theorem theorem 1 that I talked about at the beginning. So you pass everything to the injective hole, where you have this conical geodesic bicombi, and you can do your estimates. That's how it works roughly. So, right. And then back here again, so, no. Yes. So, yes, for any metric space, the following are equivalent. So X is coarsely injective, which means that every one Lipschitz map has a 1, C Lipschitz extension, so it's not one Lipschitz, but you also have constant that could be added. And X is within finite distance of the embedding into the injective hole. So remember, E here was the isometric embedding of X into the injective hole here. So you know that the injective hole is at finite distance from this embedding. Or it's equivalent to X being roughly isometric to an injective metric space. So there's no ambiguity here. Terminology is very clear. So if X is coarsely injective, then it is coarsely isometric to an injective metric space. And for this class of spaces, everything turns out perfectly. This is what you want. So if X is coarsely injective, then the following are equivalent. So X is n, δ-hyperbolic. X satisfies the slim simplex property. The asymptotic rank of X is less or equal to n. And finally, just another version of this quantification. So there exists a constant such that there is no 1, epsilon quasi-symmetric embedding of the ball in L infinity n+1 space to X. Now it's really X and not injectable. And in particular, if X is co-compact and proper, then the asymptotic rank is finite, which shows that n, star hyperbolicity is a quasi-symmetric invariant for coarsely isometric embedding, precisely because this is a quasi-symmetric invariant and so is this. Right. So I would like to end the talk with just some applications because this is all very theoretic, but I haven't talked about any spaces that satisfy this property. So I'd like to.
And the two theorems are yours with the
yes,
line, right?
Yes. These two theorems are like everything that came after the definitions are.
Can work, yeah.
Yeah. So corollaries and applications. So right. So a class of spaces that has received a lot of attention lately are Helly graphs and Helly groups. So let me just briefly introduce those. So a locally connected graph with a vertex xv, so a discrete metric space with integer valued metric, is called a Helly graph if every family of pairwise intersecting balls has a non-empty intersection. And in fact, then this vertex set is coarsely injective, and the injective hole is within finite distance of the vertex set. And right, so a group is called a Helly group if it acts geometrically on such a Helly graph. So geometrically here means properly discontinuously by isometries and co-compacting. And then it also acts geometrically on the injective hole. Right? So this was first introduced by the following authors that I will not even try to pronounce. And they show that many examples, they give many examples of Helly groups. So for example, all Garside groups, many Artin groups, all hyperbolic groups are n comma delta hyperbolic in a certain, are Helly in a certain, are Helly, and then also n comma delta hyperbolic in a certain sense. That's what I wanted to say. So we have the following theorem. So suppose G is a group acting geometrically on a proper injective metric space, for example, a Helly group, that would work. Then the asymptotic rank is finite and it agrees with all the following. So it's the minimal integer such that x is n comma star hyperbolic. It's the minimal integer such that G satisfies this slim simplex property. It's the maximal integer for which G contains an n quasi-flat. And it's the maximal integer for which x contains an L infinity flat. And furthermore, G has no free abelian subgroup of rank n plus 1. Right, and then the other application I would like to talk about is the following. Right, so-called hierarchically, it's a hard word. Hierarchically hyperbolic spaces and groups. So this was introduced in a series of papers by Berstock, Hagen, and Sisto. So basically what they do, they do some axiomatization of some results by Maser and Minsky on the mapping cross group. And it's like the definition is extremely complicated and you do not want to hear it. Right, so I will not state the definitions, but I can still talk about the results. And these HHSs, so hierarchically hyperbolic spaces, they have finite rank by definition. And for HHG, so hierarchically hyperbolic groups, it actually agrees with the maximal dimension of a quasi-flat in G. And so by a recent result of Hettel, Huda, and Petit, every such HHS admits a coarse injective metric, rho, that's quasi-symmetric to the original metric. And in case of such a HHG, then the new metric can be chosen so that G acts geometrically on this space here with the new metric, right? And then it follows that if you take such an HHG, or more generally an asymptotic, so they claim this to be just some few extra natural conditions, then you choose such a coarse injective metric rho, which exists. Then there's like the rank of the HHG or HHS is the same as the asymptotic rank, and this is the minimal integer for which the space with the new metric satisfies n comma star mu comma star hyperbolic, and it also then satisfies the slim simplex property for this constant mu with respect to eigenmetrics. And finally, so at the beginning of the talk, I said that you should keep symmetric spaces non-compact type in mind. So finally, we can say something about those. So symmetric spaces of non-compact type of rank 1 are Gromov hyperbolic. So they are n comma delta hyperbolic, n comma star hyperbolic for some star. But in high rank, this for sure cannot be true because these spaces contain Euclidean flats, and these are not n comma star hyperbolic. So the question becomes, is it possible to put a metric on such spaces so that they become hyperbolic? And by some recent result of Hettel, we can make some very easily make some progress. So yes, most classical irreducible symmetric spaces of non-compact type can be equipped with coarsely injective metric spaces, coarsely injective metric, Finster metric, which restricts to L infinity metrics on the flats. Right. So in the classification of symmetric spaces, there are spaces which are associated to the automorphism groups of bilinear forms and sesquilinear forms, and there are a few others which are called said to be of type SL. So those you have to exclude, but for everything else you can find such a metric. And the Finster metric is Beer-Lifshitz equivalent to the Riemannian metric, so the asymptotic rank remains the same. And then we can finally have the results that if X is such a symmetric space of non-compact type of rank greater or equal to 2 that can be equipped with such a coarse injective metric, then it is in fact n comma star hyperbolic, which is nice. And I would like to stop there. Thank you.